Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about nuclear reactions. In our last video, we talked about what happens when the nucleus is unstable due to too many protons. In this video, we're going to be talking about what happens when the proton to neutron ratio is not quite right. Okay, so the first one we're going to talk about is potassium 40. So if we take a look at potassium 40 on the periodic table, if I hold the periodic table up here, you will notice that potassium likes to have a mass of 39, and right now it has a mass of 40. If it has a mass of 40, that's a little bit different than what's on the periodic table. The periodic table is going to have the isotope that's most stable. So if this is 40 and the periodic table typically says 39, we're going to call this thing neutron rich because it has more neutrons than what the periodic table is suggesting that it should have as the most stable isotope. So what happens when something is neutron rich? Okay, inside the nucleus, if something is neutron rich, a neutron is going to convert to a proton. And I have these particles over here with their numbers, which talks about the mass and the charge. For a proton, the mass is 1, the charge is 1, but for a neutron, the mass is 1 and the charge is 0. So let's talk about when you have something that is neutron rich, okay, it's going to go through something called beta decay because neutrons are converting over to protons. And what I want to do is I want to write a chemical reaction for that. So let's start out with what's happening inside the nucleus. We said if it's neutron rich, we're going to have neutrons convert over to protons. So the numbers for a neutron is going to be 1 and 0. For the proton, it's 1 and 1. And as we can see, this is not a balanced chemical equation. We find out that there's a missing particle. The top number is going to be 0. So on this side, it's equal to 1, and on this side, it's equal to 1. But over here, we're going to have a negative 1 because a positive 1 and a negative 1 is what's equal to 0. So what this story is kind of telling us is that a neutron really is a combination of a proton and electron together. Okay? So if we have a neutron converting over to a proton in the nucleus, so this part's happening inside the nucleus, then it has to emit kind of like what we call an electron, which has a mass of 0 and a charge of -1. So let's go ahead and write that process going on. If a neutron converts to a proton inside the nucleus, then it has to emit an electron. And that electron is coming from the nucleus because the neutron is breaking up into its two parts, the proton and the electron. The proton is going to stay inside the nucleus, but the electron is going to be emitted. Okay, but essentially it came from the neutron inside the nucleus. Okay, so if this electron is being emitted, okay, what's the missing particle? Okay, that's kind of like the theme of the series of nuclear reaction videos that I'm making. Okay, so on the left-hand side, the mass is 40, 0 on the right-hand side, so we have to make sure we conserve our matter. Okay, and then the same thing for the charge. The charge is 19 on the left-hand side. It's -1 on the right-hand side, so 20 plus the -1 is what equals 19, which is on the left-hand side because we have to conserve our matter. When I look at the periodic table, what number has the atomic number of 20? It's going to be calcium, and we can see that if we look at the numbers for calcium on the periodic table over here, okay, that calcium has a mass of 40. Okay, that's kind of like what the periodic table is suggesting as the most stable isotope for calcium. Okay, so once again, in review, if we had to calculate the protons, electrons, and neutrons for this potassium, it would come out to be 19, 19, and 20. And if we did this, 19, 19, and 21, right? Okay, because when you add the protons and neutrons together, it has to equal the mass. We come over here and calculate the protons, electrons, and neutrons. 20 for the protons, no charge, so the electrons are 20. And when I add 20 neutrons to the protons, it equals 40. So what I'm trying to show you by doing this is take a look at what happened to the protons. They went up by 1. protons went up by 1, and the neutrons went down by 1, because a neutron converted over to a proton when it emits an electron. So inside the nucleus, these neutrons are converting to protons because it's neutron rich, okay? And when that happens, an electron is emitted, so we write about it, and when that electron's emitted, okay, a neutron converts to a proton, so now we have more protons, see, by the atomic number, and we have less neutrons. And we call this beta decay. That is the name of this chemical reaction. Beta decay takes place, okay, when you're neutron rich, okay? So what's the opposite of neutron rich? Would be neutron poor, okay? So what happens when something is neutron poor? And the example that I'm going to use here for neutron poor is going to be chromium-51. So if we take a look at chromium-51, which has an atomic number of 24, okay, if it's neutron poor, the exact opposite is going to take place. Neutrons aren't going to convert to protons. Protons are going to convert to neutrons. And there's actually two different ways that this can take place when you're neutron poor. Let's talk about the first way. So if it's protons to neutron, right? What's the missing particle? Well, let's do our numbers. 0 would be the top number, and the bottom number would have to be 1. What particle has 0 and positive 1? It's going to be this thing called a positron. So this is what's happening inside the nucleus, and this is what's going to be emitted from the nucleus. So let's go ahead and write about that. The top number is going to be 51, because 51 plus 0 is the same thing as 51. What number plus 1 is going to be 24? It's going to be 23. So 23 plus 1 is going to equal 24, and 23 up here is vanadium, okay? So we call this positron emission. So let me write that down. Positron emission, okay? So positron emission happens when something is neutron poor. So when it's neutron poor, it emits a positron. When it's neutron rich, it emits an electron. When it emits an electron, neutrons convert to protons. When a positron is emitted, protons convert to neutrons inside the nucleus, okay? Well, there's another way that this can take place, okay? It can take place through capturing a particle as well. So I'm going to do this again. Proton converting into a neutron, but instead of emitting a particle, it's going to capture a particle. So we put it on the left-hand side of the arrow. Well, what particle does a proton have to capture in order to become a neutron? Well, if we follow the numbers, the top number has to be 0. The bottom number has to be -1, because 1 plus a -1 is what's equal to 0. And it looks like, what is 0 and -1? 0 and -1 is the electron. So we're going to call this electron capture, okay? So when we capture this electron from a proton, with a proton, the proton converts over to a neutron. And that's basically what's happening here. Protons are converting to neutrons in both places, but it's doing it different ways. This way, it's through the emission of a positron. This way is through a capture of an electron. So I want to take the same chromium-51 that's neutron poor, chromium-51 that's neutron poor, and instead of expelling or emitting a positron, I'm going to add an electron to it. I'm going to capture the electron, and let's see if we get this vanadium-51 answer. So the top number on the left, it's 51, so this has to be 51. On the right-hand side, 24 plus a -1. On the left-hand side, well, that has to be 23. Well, how about that, okay? We get to this vanadium-51 answer both ways, either through the emission of a positron, okay, or through a capture of an electron, both ways will convert a proton to a neutron. Because you're neutron poor, we will need to make more neutrons. That's why the proton is converting over to the neutrons. And this gives us balance, okay, to our proton to neutron ratio, okay? And if you find that video helpful, please do like and subscribe. And please add a comment, because that does help the YouTube algorithm.